Hi folks, welcome to the Chapter 7 Concept Roundup for Math 621B. In this roundup we're talking about exponential functions and equations. As always, there's a link to downloadable notes and a review in the video description below. Here are the four basic topics we'll look at in the course of the video, and let's dive right in. When we mean an exponential function, we mean something like this: y equals c to the power of x. Some number to the power of x. And there are basically two scenarios you might encounter. You might have y equals the power of, say, y equals 2 to the power of x. So you've got a base of 2 here. This will indicate an increasing function. If instead we have a number that's less than 1, like a half to the power of x, what we'll end up with is a decreasing function. Now, both of these functions are going to have an asymptote of the x-axis, and they're both going to get steeper and steeper either as we go to the right or to the left. So we're increasing if c, or the base, is greater than 1. We're decreasing if the base is between 0 and 1. And if the base was less than 0, if it was negative, then these would all be extremely poorly behaved. So we only really want to talk about positive bases. The domain, you can put anything you like in here. And the range is going to be y is greater than 0. You're always above the x-axis. Or you could call that y is a positive real number. There's a y-intercept on these basic graphs of 1. And that's because anything to the power of 0, except 0, is going to give you 1. So y-intercept of 1, no x-intercept. And the x-axis, which is the line y equals 0, is an asymptote. The curve gets infinitely close, but never touches. So in its most basic terms, something like this: y equals 4 to the power of x. We'd know that that's an increasing function. It goes through a y-intercept of 1, gets steeper and steeper to the right, and asymptotic to the x-axis on the left. Now that we've got the basics, we're going to transform them. And we have our typical set of parameters that we can work with. So we could have a vertical stretch factor. That's what a does here. And it would be by a factor of a. If you had a negative a value, this could be an x-axis reflection. C is just our base. It determines growth or decay. B is our horizontal stretch, and it's always by a factor of the reciprocal of b. And it can give us a y-axis reflection if b is negative. H, that's our horizontal shift or translation. And K is our vertical shift. And K also controls where the asymptote is going to be. So the asymptote will be at the line y equals k. Usually it's just on the x-axis, which means y equals 0. If we're shifted up, then the asymptote is going to be shifted up accordingly. When we sketch transformed exponentials, first of all, some of these parameters up here, the a, b, h, and k, some of them are redundant. So we don't really need that many to define any exponential graph. We can talk about all the transformations in a given graph, but the easiest way to go about sketching them is to sketch the asymptote, which is going to come from this k value, your vertical shift. Find 2 or 3 points just using a table of values, because they all look either like this or like this. They look like bananas. And then we'll connect smoothly. So using that idea, we're going to describe and then sketch each one of these ones. So right here, we've got a negative as our first term. So that means x-axis reflection. We have an x plus 1. Well, that's going to be moving left 1. If you want to think of it that way. Now, there's nothing that is added on at the end. So the k value is 0. There's no vertical shift. So when I do go to graph this, I'll know that the x-intercept, or rather the x-axis, is the asymptote. All right, now all I need is a couple of points. And choose x values that are easy to work with. So I might choose 0 for an x value. If I put in 0 into this whole function up here, I'd have negative 4 in brackets to the power of 0 plus 1. So that's 1. 4 to the 1 is 1. Make it negative. So right now, I know that the point 0, negative 4 is on this curve. I could pick 1 for x. Looking at it, though, I might find negative 1 more convenient. That means I'd have negative 4 to the power of negative 1 plus 1. That's just 0. 4 to the 0 is 1. Make it negative. You have this point. Negative 1, negative 1. Okay, now I know that the x-axis is an asymptote. I just connect these smoothly. X-axis is an asymptote. The equation of that asymptote would be y equals 0. That's what the x-axis is. Now, you could have chosen different points. It doesn't matter. There are infinitely many good points to have chosen. All right, let's try the next one. We have y equals 3 times 2 to the negative 2x plus 2 minus 5. Now, if you're thinking about your Chapter 1 material, you might say, hold on now. Coefficient of x should really be factored. So this should really look like this if we wanted to describe and have a good order for a description. Okay, so what is this telling us? Vertical stretch by a factor of 3. The negative 2 would mean horizontal stretch by a factor of a half. We have a y-axis reflection. We're right 1 and down 5. Now you can produce the graph without making all of those descriptions. The only one that's really important to understand is the down 5. Because here's what that's going to do for us. It means when we go to graph, I know I've got an asymptote at negative 5. Okay, so here's my sketch. 1, 2, 3, 4, 5. And if you looked at the steps up here, it would say, step 1, sketch the asymptote. Okay? Next, we're going to come up with a table of values. And again, we'll just choose some easy values to work with for x and y. Okay. So maybe I'll choose 0 again. If I chose 0, I'd have 3 times 2 to the power of negative 2 times 0 is 0 plus 2. So what would that give us? That would be 4 times 3 is 12 minus 5 is 7. So 0, 7 is on this graph. 1, 2, 3, 4, 5, 6, 7. There we go. Maybe I'll choose 1 for my other point. Okay? And if I'm going to do that, then I would have 3 times 2 to the power of negative 2 plus 2. That's 0. Okay, so 2 to the 0 is 1 times 3 is 3 minus 5 gives me negative 2. So the point 1, negative 2 should be on here. Okay. And now all we need to do is sketch. Connect our points smoothly. The asymptote is now that dotted line. And the equation of that dotted line is y equals negative 5. That's the equation of the asymptote. Now you might have said, well, this was supposed to be growth because this is a 2. It's a number bigger than 1. But notice that it also got a y-axis reflection. So that flipped it around. Okay. So we can graph these without describing. We can just go to the table of values, but you do need to be aware of the asymptote. Here's another case we might run into, trying to figure out the equation from the graph. So the function takes the form y equals c to the power of x plus k. K is the vertical shift. So let's take a look at this. It's got an asymptote on y equals -3. That's going to be your k value. Been shifted down 3. And it's the same as the asymptote. Okay, if we keep going with that, we want to find c now. One of the easiest ways to do it is to sub in a point. And let's choose the point 2, 1. Okay. So now we know y would be 1, c is still unknown to us, x is 2, and k is -3. Now we've got an equation with only one unknown. So no big deal. That gives us c squared equals 4. Usually we'd say c is plus or minus 2, but the base in exponential equations needs to be positive, so c must be 2. That means the equation of this function should be 2 to the x minus 3. All right, let's find out. I've got it hidden behind here. There it is, 2 to the x minus 3. We did an awesome job. We figured it out. Okay, so vertical shift is your k value. Okay, word problems that stem from exponential growth and decay. There are a lot of things in nature that either increase exponentially or decrease exponentially. And there are a bunch of ways that we can think about a general formula for describing them. This is the way I like. P in this formula, and it's pretty full service. It can deal with a whole bunch of different situations. P is your final amount of something. It might well be population, but it could also be value in dollars. It could be number of cells. We don't really know. PO is the original amount or initial amount. C, the base of your exponent, that's going to be your growth or decay factor. And we'll look at what that does in the context of a few questions in a minute. Then we've got this t. T is time elapsed, the amount of time that's passed in the question. And then I spent a long time trying to figure out what the right letter is to use here for what goes on the bottom. And we have so many letters that are arbitrarily being used to describe a bunch of other stuff. In the end, I just went with smiley face. And here's what smiley face means. It's the time for one described change. So often these questions will say per year. In that case, smiley face is 1. It's per 1 year. But it might also say something like the population doubles every 23 years. In that case, smiley face is 23. It's the amount of time for that doubling or that described change to happen. Here we go. Let's take a look. The population of Stratford is 8,600 and is increasing at a rate of 5% per year. Write an equation for population growth. So we need to figure out what each of these values are. That 8,600, that's our initial amount. So if I wrote an equation, it would go like this. Population after some time is 8,600. Now, it's increasing at 5% per year. That means every year, there's 100% of what the previous population was, and another 5%. That would be 105%, or as a decimal, 1.05. That is your C value. That's what you're multiplying your population by every year. It's getting 1.05 times bigger. If we had just times it by 0.05, well, the population would be getting smaller, and that wouldn't make sense. So it's 100% of what you had plus another 5%, meaning 1.05. Okay? T is unknown to us at this point, and since it says per year, smiley face is 1. So we can call it T over 1, or just T. Now, we'll find the population in 5 years. So that means substituting in 5 for T. Okay. We go to our calculator. 8600 times 1.05, all to the power of 5, 10,976 people is what we project. Let's try a few more of these using that general formula. The value of a 2002 Toyota Echo is currently about $1,500 and is depreciating, that means decaying, at a rate of 15% per year. So, the general formula was P equals PO C to the T over smiley face. We can probably pick out what's going on with PO. It's the original amount of 1,500, or the initial amount. Now, the rate, let's think about this. It's losing 15% of its value every year. That doesn't mean it's worth 15% as much every year. It's just gone down by 15%. So what we should think here is that it had 100% of its value and it lost 15%. It has 85% of its value left. If you wanted to find out the value next year, you'd multiply 1,500 by 0.85. If you multiplied it by 0.15, it would be decreasing way too fast. So that's the base of our exponent. T is unknown, and per year means smiley face is 1. So we don't really need to show it. If we want to find the value in 3 years, well, we just throw in 3 for t. And let's see what we get. Come on, big money. Oh, $921.19. That's rough. But I did love my Toyota Echo. Population of a colony of bacteria is currently 50 cells and multiplies 4-fold in 2 hours. We're going to write an equation for the bacteria population after n hours. Or we could call it t hours. Let's call it t hours. Okay, so right now there are 50. That's our PO. 4-fold. That means it gets 4 times as big. You multiply your current population by 4 to make that happen. So if you see 4-fold or 3-fold or 2-fold or doubles, that's telling you exactly what the base of your exponent is. Okay, here t is unknown to us, but this thing happens every 2 hours. That's the smiley face. That's the time for one of these described changes. What will the population be after 1 day? So here's what we'd be tempted to write. Put in 1 for t. But remember that we did our smiley face in hours. That means we need to do our t in hours as well. We have to have a common unit of measurement. So I'd put in 24 for 24 hours in 1 day over 2. Now, don't give your calculator the opportunity to mess you up by putting in 24 over 2. We know 24 over 2 is 12. Whoa, that's a big number. It's a lot of bacteria. So we get 838,860,800. Yowza. But that's the nature of exponential growth. Stuff grows, and then it grows upon its growth, and it grows faster and faster and faster. Last one, cesium-137 has a half-life of 30.17 years. What that means is that in 30.17 years, half of the sample that you have is going to decay and no longer be cesium-137. It's an unstable isotope. From a 10 milligram sample, how much would remain after a century? So this is a classic example of exponential decay. Now, you can see here that 10 is going to be your original amount. Whenever we talk about half-life, our c, or our base of our exponent, will be a half. Okay. Has a half-life of 30.17 years. That's telling us how long it takes for one of these halvings. So that's actually the smiley face. The amount of time that's passed is 1 century, or 100 years. When I put that in my calculator, I'll make sure I put my power in brackets. So it'll know to raise it to that power rather than raise it to just one of those numbers and then divide. So 10 times 0.5 to the power of, brackets, 100 divided by 30.17. And after a century, still 1/10 of it, or 1 milligram, remains. The question we haven't been able to answer here is a question like, after how many years will 3 milligrams remain? But we'll deal with that once we hit Chapter 8. Okay, moving on. Exponential equations. Exponential equations are literally equations where the x, or the variable, is in the exponent. So we're going to solve, and we'll check just to make sure we did a good job. And here's the method. You need to convert to a common base. So right here I have a base of 2 and a base of 8. That's not that helpful. Let's see what we can do with those. So we'll do kind of step 1 here. 2 to the 3x minus 1. I can express 8 as 2 to the power of something. 8 is 2 to the 3rd. Great. So I've done this. Often we have a prime. It's not necessary, though. Okay, now let's think about this. The base is the same. The whole thing is the same on both sides. That means the exponents must also be the same. So we're just going to equate our exponents, or get rid of our bases. So I'll say this. Therefore, 3x minus 1 must equal 3. That's from the exponents. Okay, now I can solve. That's pretty easy. 3x equals 4. X equals 4 over 3. I wonder if that is actually true. Let's check. On the left side and right side. Right side should be 8. Left side I would have 2 to the power of 3 times 4/3 minus 1. 3 times 4/3 is 4 minus 1, or 2 to the 3. Hey, it works. We get 8 on both sides. Okay. So, convert to a common base, equate the exponents, and solve. Now you might be thinking, well, what if there's no common base? What if you had 2 to the 3x minus 1 equals 7? Then we're in trouble. We'll need logarithms, and we'll deal with that in the next chapter. But as long as there is a common base, we can use this technique. All right, so the next one, we've got 2 to the 4x and 4 to the x plus 3. Look at those two bases, a 2 and a 4. Can they be expressed as something common? Well, the number 4, another way to write it is just 2 squared. And I'm going to make that my whole first step. All I'm going to do is take the number 4 and write it as 2 squared. Everything else stays the same. Now I know when I have powers to powers, I multiply them. So I'm going to need to multiply this 2 by x and by 3. That gives me 2 to the 2x plus 6. Now we have a common base. We're going to equate the exponents. You can write it with the therefores or not. Doesn't matter. 2x equals 6. X equals 3. You can go and check it, and it will work out for us. Now we do have to know our exponent rules fairly well to be able to find that common base. So I have a 1 over 9 in the next one, and a 27. What's fishy about these? 27 is 3 cubed, but can I express 1 over 9 as something to do with 3? You certainly can. It's a 3 that's flipped over and squared. That means it's a 3 to the negative 2. 27 is 3 to the 3. And notice that in this first step, all that I did was rewrite 1/9 as 3 to the negative 2 and 27 as 3 to the 3. Didn't try to combine any steps. And my experience has been that that saves a lot of pain. Okay, now we've got a common base. We've dealt with our exponents, multiplied them on the right-hand side there where we had powers to powers, and same on the left-hand side. Now we can get rid of the bases and say negative 8x equals 3x minus 3. Or negative 11x equals negative 3. Divide both sides by negative 11, and you get x is 3 over 11. And again, you can go back and you can verify this will actually work. Okay, the last topic we'll take a look at is compound interest. Compound interest is exponential growth. It just has its own sort of conventions that we want to be a little bit aware of, because you're definitely going to have to deal with compound interest at some point in your life, whether it's paying off credit card bills, whether it's taking out a loan, or making an investment. So compound interest is exponential growth. And you would think that if you saw 30% interest over the course of a year, that if you put in $100, you would either have or owe $130 at the end. That 30% would mean you'd have 30% more either in debt or in your bank account. But because of the different ways that you can compound that 30%, it may end up being a little more than that. So that 30% is what's called the nominal or named rate. But it's not the true effective interest rate. The effective interest rate depends on how many compounding periods are in a year. So whether it's weekly, monthly, semi-annually, or whatever. Here is one formula for compound interest. Now, if you fish around on the internet, you may find other formulas. Some of them have more letters in them, and some of them have this amount of letters in them. In here, we have to figure out I and N ourselves. It's not built into the formula, but there are fewer variables to deal with. So A is the final amount. P is what we call the principal, or the original amount. So already it's looking a whole lot like our P equals PO formula. I is the interest rate per compounding period as a decimal. And what I mean by that is if you see 10% and it's semi-annually, then I is going to be that 10%, but it'll be divided by 2, because semi-annually means 2 times per year. Which is 5% or 0.05. N is the number of compounding periods. So if I had the same situation, if I had 5 years, but we got compounded semi-annually, then N would not be 5. Semi-annually means twice per year. So N would be 10, or 5 times 2, 2 times 5. Twice a year for 5 years is 10 compounding periods. Let's try and put this to use. So imagine we have a $5,000 investment. We're going to put it in for 3 years. It earns 4% per annum, that means per year, compounded semi-annually. So right here, this word is important. Twice per year. Okay, just down here I'm going to write the formula A equals P, 1 plus I to the power of N. So I can pick out some stuff. This right here is the principal, the original amount that we have. So I'd say A equals 5,000. 1 plus that I. I comes from the 4%. But since it's semi-annual, which means 2 times per year, you divide it by 2. Okay? Which makes for 2%, or as a decimal, 0.02. Similarly, the 3 years helps determine N, But it's 3 years twice per year. How many compounding periods is that? That's 6. 2 times per year for 3 years makes 6. Or 3 times 2 we could think of it as. Okay. Plug it in. Here's what we get. 5,000. 1 plus 0.02, all to the power of 6. $5,630.81. Okay, so your money made $630.81 just by leaving it in this investment. Let's look at stubborn Eric here. Refuses to pay his credit card, which has a 30% interest rate compounded monthly. Now, if you refuse to pay your credit card for a full year, chances are they will jack up your interest rate, and you won't be able to get away with just ignoring it for a full year. Currently, he has a balance of $1,000. How much will he owe in 1 year's time? If compound interest worked the way we want it to work, then the answer to this question would be $1,300. It would be 30% more than $1,000. Okay. But the effective interest rate turns out to be more than that. Let's figure out what's going on here. So A equals, principal is 1,000 here. 1 plus I. Okay, here's the important bit. It's monthly. That means 12 times per year. So I is going to be 30%, but divided by 12. That makes for 2.5%, or 0.025. Now let's figure out n. He goes for 1 year, but it's compounded 12 times. So how many compounding periods is that? Well, it's pretty straightforward. That's 12. Okay, if he leaves it alone for 1 year, it'll be calculated 12 times, or once for every monthly bill. We throw that in our calculator, and I already did, and we get $1,344.89. So instead of being charged 30% in the end, it works out to be more like 34.5%. That's the difference between the named rate, or the nominal rate, and the effective rate. Okay, one last one just for a little thought here. John invests $1 in some amazing investment opportunity which earns 100% interest. Find the value of his investment after 1 year if it's compounded quarterly. Okay, so we'll set this up. A is going to be $1, 1 plus. Quarterly. That means 4 times per year. So I will be 100% divided by 4, or 25%, or 0.25. N will be that 1 year times 4 times per year. Let's see how much he makes. To the power of 4, $2.44. So he made $1.44. Exciting stuff. Now, if it only had been compounded once in the year, he would have only made $1. He'd have $2 at the end. So by compounding a few times, he made more money. Let's try this again weekly. And hopefully by now you can see the pattern. The I is going to be the 100%, which is just the number 1, divided by the number of times it happens in a year. This would be 52 times per year. It happens for 1 full year, so the n here would be 1 times 52, or 52. Let's see if he makes more or less money. One divided by 52, all to the power of 52. Ooh, he makes more money. So it looks like the more you compound, the higher this value gets. And you might think if you did this 1,000,000 times or 100,000,000 times or 1,000,000,000,000 times that you would make infinitely much money. It turns out that there's actually a limit to how much money you can get, and it leads to a very special number that we're going to explore in the next chapter. I hope that you found this helpful, and good luck with your studies. Again, you've got a review that you can download in the notes that are just below. Take care.